Welcome. The purpose of this lab was to analyze the motion of a spring mass system in which a mass of 0.402 kilograms swings in an arc while oscillating on a spring. In order to do so, a video of said motion was examined in Tracker to produce a set of data points describing the observed motion, and then Python was implemented in order to produce a set of data points describing the predicted motion that was used. The Python code was constructed using two fundamental principles, Newton's second law and the energy principle. Assuming these principles are accurately executed, the predicted and the observed motion are an almost complete match, as will be shown later in this presentation. Shown is the completed video analysis. In order to obtain information on the observed motion, the video is first uploaded into Tracker and then it is analyzed frame by frame, starting at the moment of release in order to gather the specific points. However, before we could analyze the video, a calibration stick, shown in blue, was set for the distance between the connection point and the center of the mass, and axes, shown in purple, were put in place so that the connection point became the origin of the xy plane, with the spring running down the negative y-axis. Once the video was analyzed, the time versus position plots and the table of the data points were used alongside Newton's second law in order to solve for initial conditions needed for the Python code. Newton's second law states that F net equals ma, which can also be written as F net equals the sum of all of the forces acting on an object. Using this fundamental principle, we look for the net forces in the spring mass system. In this case, there is a gravitational force, which is equal to the mass times gravity, and the force of the spring, which is equal to the spring constant times S, which is L minus L naught. This principle is then used to solve for the spring constant and L naught. Using the time versus y plot in Tracker, it is gathered that our video goes through 5 periods. We then use this fact to solve for the average period of the oscillation and use this value to solve for the spring constant based upon the formula period equals 2 pi times the square root of the mass divided by the spring constant. As shown, the spring constant is 6.706. To solve for L naught, we can use the fact that at the bottom of an oscillation, F net is equal to 0, and thus we can solve for L naught by setting the force of gravity equal to the force of the spring. L naught is then calculated to be 0.1125 meters. When we use Newton's second law to be F net equals ma, Newton's second law can then also be expanded to solve for position and velocity. The energy principle is the other fundamental principle used. In its simplest form, the energy principle states that the change in energy is equal to the change in kinetic energy plus the change in potential energy. This can then be expanded to say that the change in energy is equal to the change in kinetic energy plus the change in gravitational potential energy plus the change in potential energy for the spring. The energy principle will be implemented in the Python code in order to show how the energy of the system changes over time. Also, work is equal to the force times the change in R, which is equal to 0 in this case. And we know that change in energy is equal to work. It can then be said that the change in energy is equal to 0. These concepts will all be seen in the code. There is now enough information to set the initial conditions in the Python code. First, the mass of the ball is set to 0.402 kilograms. Then the ball position is added using the first data point, which is negative 0.114, negative 0.645, 0, and then the velocity is set to 0 as the mass starts from rest. After that, we add in the values that were calculated for the spring constant and L naught. Then principles of a spring system are applied in order to calculate for L, which is the ball's position minus the spring's position, L hat, which is the directional component needed to compute the spring force, and S, which is L minus L naught. Then the net interactions are added with the force of gravity being equal to the mass of the ball times gravity times the vector 0, negative 1, 0, the spring force being equal to the spring constant times S times negative L hat, which is L divided by magnitude of L, and the net force being equal to the summation of the gravitational force and the spring force. Using the formulas for velocity and position that were derived from Newton's second law earlier, the ball's position and its velocity can be calculated. Next, we deal with the system energies using the formulas for kinetic energy and potential energy. First, we have the kinetic energy equal to 1/2 times the mass of the ball times the magnitude of the velocity squared, the gravitational potential energy as the mass of the ball times gravity times the ball's position, and the potential energy of the spring equal to 1/2 times the spring constant times S squared. These values can then be used to calculate the change in energies by setting delta K equal to K minus K initial, delta UG equal UG minus UG initial, and delta US equal to US minus US initial. For the energy plot, the blue line is the change in kinetic energy, the red line is the change in potential energy of the spring, the green is the change in energy of the gravitational potential energy, and the yellow line is the total change in energy. This graph shows that the change in energy will always be equal to 0, as well as the fact that the energies oscillate similar to the position of the mass. For the predicted versus observed plot, the predicted motion is shown in blue and the observed motion is shown in red. The two paths nearly line up perfectly. Discrepancies are most likely a result of the manner in which the points were chosen in the tracker analysis. For example, the points may not be fully aligned with the center of the mass suspended on the spring. What does it mean, part 1? Based on the energy plot gathered from the first simulation, it can be seen that the energy principle is satisfied. The energy principle states that work is equal to the change in energy. Using the fact that work is equal to the force times delta R, we can see that the work is equal to 0 because our system is the Earth and the system itself is not moving. Therefore, the change in energy must also be 0. This is proven by our model, as the change in energy, represented by the yellow line in the energy plot, is at a constant value of 0. What does it mean, part 2? As seen by these calculations, when we make two separate calculations for the period of oscillation, our values are slightly different. The period in the x direction is 1.63 seconds, and the period in the y direction is 1.56 seconds. This is because in the x direction, the only force acting on the mass is the force of the spring, whereas in the y direction, there is both the force of the spring as well as the force of gravity. Conclusion. In conclusion, it is possible to predict the motion of a spring mass system rather accurately when Newton's second law and the energy principle are implemented. Thanks for watching!